So, hi everyone. So in this video I'll going to explain the basic common source circuit where the PMOS is used as a current load or active load. So first let me invoke the Cadence tool. Just right click and go to terminal. First invoke CSH, then invoke the Cadence source CSH RC. Then you have to set the path. So CD space home Cadence. Then here my folder is my libraries. I'm using test VLSI folder, so I'll going to invoke that. So once you have set the path, so you have to invoke the Virtuso tool, right? So in order to invoke that, Virtuso is the command, right? So once you have invoked the Virtuso, just close this. It's just a welcome window. Close this. Now using this, so what you have to do? So you have to go to File. In the file, go to New. In the library, I think the library is already created in the previous experiment, so you don't have to create one more time. Just go to cell wave. So you have to create. You are creating one more experiment. Let's go to cell wave. In the cell wave, so test1 is my library which is already created. So I'll just give the which is created in the previous lab. So I'll just give the new name for common source experiment. So let it be common source underscore schematic. Okay, so just view schematic, just click OK. Fine. So now I can see the window, right? So I think in this video I'll not going to split the steps. So analog design steps I'll not going to split. So I'll going to explain complete PreLayout simulation in one stretch, so in one video. So this is so in this now, so we have to add the instances for common source. So again for common source here the PMOS is used as a active load or current load. So first I have to go to create instance. So in the instance I have to search for GPDK45 components, right? So in this, so I have to search for PMOS version 1, right? That is symbol I need, right? Just close this, just hide and place PMOS. In the same way I need NMOS also. Again I'll go to instance, I'll select NMOS, browse, select NMOS version 1. So just close this, hide and place NMOS. Fine. So once you have done, so I need the pins. So once you have added the instances, next I need the pins. Just select pin P. I'm sure I'm using the shortcut, or you can go to create and select pins. That is also okay. Fine. So here I have to give the name. First I'll give V in. So you can give all the V input ports on one stretch, input pins. So I'll just give V in space VDD and uses VSS. Right, I have given all the 3 pins on one stretch. Just hide this. Now this is the first is by V in. I'll place here. Next is VDD I'll get. So I just rotate this. R is the shortcut to rotate the pin. I'll rotate and place here. Again one more is VSS. Again I'll rotate this and place it here. Right, all these pins are selected on one stretch, right, by typing V in here, right, because all pins are same. So or you can do it one more time, so one by one also we can type. Right, now I need V out, so I'll type that. So this direction is output. Now hide and place the output pin, right? So this is now I've added the instances PMOS as well as NMOS, and I've ordered all the input output pins where VDD, VS, VIN, VSS as well as VOut as the input pins, and we have left with one more pin. I'll just keep this V in here, right? So because here PMOS is using as a active load or current source, here I need the biasing point because all the time my PMOS should be on all the time, right? That means it should be in active region so that I can have a sufficient output on the other side, because common source is basically a voltage amplifier, right? I know you people know that, right? Basically voltage amplifier, so common source. So I need biasing here again, that is also another input. So I'll go to create again, I'll create pin, so V bias, I'll give the name as V bias. It is also an input, so just hide and place the V in here. Okay, now I've added both all the pins, V in, V bias, VDD, VSS as well as Vout. Now the step I left with is the connection, right? So what I have to do, I have to go to create. In the create I have to select wire, or shortcut is W. Select wire and connect all the pins. So VSS I have connected, so NMOS is connected to VIN, right? V bias is connected to PMOS, and drain and drain is connected, so that should be connected to Vout. So I have connected. Then so VSS VDD has to be connected to PMOS source, right? So now we have connected, and again we have forgot to connect the substrate connection. So I'll select that. This is the substrate connection, right? I'll do that first. Now I have done the substrate connection also, right? So this is the circuit diagram for, or schematic circuit for, common source, where the PMOS will be acting as a active load by giving a bias voltage to it. So it will always be in active region, so that the sufficient voltage will be amplified at the output, whereas NMOS is used as an input. Fine. So basically a common source is a voltage amplifier, right? So we'll get some gain at the output. So now this is the first step. So the writing the schematic, I'll just save and check for the errors, and I'll save it. Now the next step is, so I have to create the symbol for this, right? So what I have to do, just go to create. In the create, go to cell view. In the cell view, select from cell view. Okay, so in the from cell view, so let it be the library name test1, cell name let it be the same, common source schematic. So from schematic I want to view the symbol, so just click OK. Once you click OK, so as I said, it will ask for the pin configurations in the symbol. So how you want your pins, on the left or top or the right or the bottom, right? So for my convenience, for the future circuits, for amplifiers, for differential amplifiers and op-amps, operational amplifiers, so what I'll do is, because the same module will be used in the future experiments, because of that I'll keep V bias pin on the bottom as well as VSS pin on the bottom, V bias as well as VSS on the bottom, whereas VDD on top and VIN on the on the left pin. Okay, just for the connection convenience, I'm using V bias in the bottom. Okay, because in this circuit actually V bias on the left side, so you can do that also, you can create the same also, but for a connection convenient purpose, I'll keep V bias in the bottom. Okay, just click OK. So it has generated the symbol for the circuit. So if you observe here, VIN is on the left, VDD on the top, Vout on the right, and V bias and VSS on the bottom. Okay, so you can change its the structure also, as we have seen in the previous video, or if you keep the same, that is also okay. So I'll not going to rewrite or change this structure. I'll keep the same here. Okay, so just save this, just save and close this. So now I have created this symbol successfully and I have saved it. Now what is the next step after creating the symbol? So we have to create the test circuit for the same, right? For this we have to create the test circuit for verifying its results, right? So how do we do that? So we have to go to file. For creating a test circuit you have to create a new cell wave, right? So I hope you remember this step. So you have to go to file, in the file select new, in the new. So now we have CommonSource schematic. So instead of schematic I'll use test, right? This is another cell name for creating the test circuit, because the same circuit will be used for post layout simulation also, right? For that, so I'll give a new name for test circuit. I'll just click OK. Fine. Now what we have to do in the test circuit, so you have to import that CommonSource symbol that we have created just now. Okay, so how to import that? Go to create add instance. In the add instance you have to search for the, you have to browse for the corresponding symbol. So my library is test1. In the test1, so I have the CommonSource schematic, right? You have the symbol already, right? CommonSource schematic symbol is already there. So I'll just close this, hide, and place the symbol, right? This is the CommonSource schematic symbol, right? For this now I have to add all the values. Okay, that means I have to connect all the analog components, then I have to search, check for the results or verify for the results, right? So how do we do that? First we'll add VDD, V bias as well as VSS, because all are DC voltages. So I'll just give VDD, VSS as well as V bias first, then I'll give V in, then V out. Okay, so first we'll create, go to create instance. So we have to search for the corresponding, so we have to search for the corresponding circuit, right? So where is my set? So it is in analog lib. So in the analog lib I have to search for VDC, right? So select VDC symbol, just close this. So in the symbol, so DC voltage, so let me give it as 2.5 volt. Okay, so this is the DC voltage. So hide this, just place the VD pin here. Again in the same way I have to go to add pin, so add instances. Again I need VDC only, but instead of 2.5 voltage I need to give minus 2.5 volt for VSS. Okay, so hide, so I'll place minus 2.5 volt here. Okay, so this is positive 2.5 and this is negative 2.5 volt. Now again add to instance. In the instances, so you have to go to again VDC only. So for V bias voltage, so here let me give it as minus 1.1 volt. Fine, I'll tell you why, because so V bias voltage is, so let me give V bias as 1.1 volt. So I'll just place up here. Okay, so make sure that, so you may ask why we have to give 2.5, VDC is 2.5 and VDC for V bias is minus 1.1 volt only, because here in this circuit if you observe here I'm using PMOS as current load or active load, right? That means I need to give at least, so because it's a 45 nanometer technology, at least I need to give 1.1 volt for setting up the channel between P in a source and drain in the PMOS. So because PMOS requires a negative volt of minus 0.1 1.1 volt, because it's in order to turn on this I need to give a negative voltage, right? For that I am giving it as 1.1 volt. Means what is the meaning of this is, in 45 nanometer technology, this is the minimum volt that is required to keep the PMOS in active mode. Fine. And in order to have a sufficient, okay, sorry for that, in order to have a sufficient voltage across this, so VDC must be at least sufficiently large than your V bias voltage, right? So at least half of that should be higher. That means it is much higher than V bias, so that's why I have given it as 2.5 volt. Okay, so this is with respect to VDD, VA bias and VSS. Now, so I have to give input, right? V in, right? So I have to search for V in because it is analog. So in previous, in inverter we used V pulse. Here we cannot use that. Instead of we use V sine, SIN. So this generates the sine wave, right? Sine wave source. Just close this. Here you have to give the voltage. Fine. So for AC magnitude, DC voltage, don't give any voltage DC, because it's a AC magnitude, AC voltage we are trying to provide. So AC, it is, let me give it as 1 volt, let it be 1. And so magnitude, so amplitude is asking, so amplitude, let me give it as 5 millivolt. So around 5 millivolts I am giving. So peak to peak I'll get 10 millivolts. Fine. So then it is asking for a frequency, so let it be 1k, 1 kilohertz. So just have to type 1k, so hertz it will take automatically, right? See this like this. So how much I have given? I have given AC magnitude, amplitude 5 millivolt, right? That is positive. So peak to peak if I take, I'll get 10 millivolts peak to peak. That's it. So I have given the frequency, right? Just hide this and place V in at this point. Okay, now I've added all the components, so I just have to add the pin, output pin, right? So go to pin. In the pin I have to type V out, so the direction is output. Just hide this and place V out here, right? So in this area you cannot place any component, so just I put all the components outside. Now I have to connect it. So before I connect, I need to add the ground, right? For all the components I need to have the ground. For that, so I'll select add instance. In the instance I have to search for ground, GND. This is the ground. Just close this. So I need one ground here to V in, then to VDD, then to VDC, also for VDC VSS, right? Need to add a ground for all. I just added it. Now I need to connect all. So what I have to do, I'll go to create and select wire, right? So using wire I'll connect all the pins. So positive of VDD should be connected here, so I'm connecting it. So V out, then V bias to V bias, then V in. So just connect it, right? So I've given the input, then VDC I have connected V bias minus 1.1 and VSS is minus 2.5, then output, right? This is the test circuit, so you have to create for verifying the common source. Now I'll save it, check for the errors and save it. I have saved it successfully. Now to perform the simulation, so we have to launch the analog environment, analog design environment. So how do we launch that? Go to launch, select ADEL. Fine, analog design environment should be launched. So just select that. So here I have to select for, I have to set up the analysis, right? So what are the types of analysis you want to check, right? So I'll go to analysis, go to choose. In the choose option First I'll select transient. Fine. So in the transient here, let me give it as around because I have given 1 kilohertz, it is 0.5 milli, so I'll give it around 5 milliseconds, 5 m. So results, I need accuracy results on moderate, right? And this is the transient analysis from input wave to output. I want to check that I have selected. Just apply this. So now it has appeared. So transient analysis. Now I'll select DC. Again DC also same thing. You have to select operating point, then design variable, sorry, component parameter. The component meter parameter, you have to select component, V in DC voltage, select. Now come back. Fine. Now you have selected the DC component. Sweep range, here I have given maybe from 1.12, sorry, minus 2.5 to 2.5 you can give, because VDC is up to that range I have given. So you can give minus 2.5 to 5 plus 2.5, you can give the sweep range. Fine. Or you can give minus 5 to 5 also, because input voltage is up to that, so you can give that also. So give it, then select, save, apply. Sweep range, let it be automatic, just apply here. So DC also selected, or you can give this value as 5 to 5 also, minus 5 to 5 also you can give. Fine, because DC analysis, no, so you can give either 5 to 5 also. Okay, now we have to select AC analysis also, because we have a AC signal, right? We have to select the AC analysis also, because we have to plot the magnitude of AC. So we have to select the sweep variable frequency. So it is asking for the frequency range, start and stop range. So I'll select from 100 Hertz to around 150 megahertz. So 150 m is the megahertz. I'll select. Now it is sweep type it is asking, so usually the magnitude will be placed in the logarithmic values, right? So logarithmic points per decade, I'll give it as 20. Okay, 20 dB, because voltage, right? So obviously you need to measure it in 20 dB, so 20 log, right? So the points per decade is 20. Now apply and click OK. So now in the previous inverter we have selected only transient, we have checked for transient and DC analysis only, because the input itself is DC, that means in other words it's a V pulse, so that's why. But in this case, so we have used V sine, analog signal, sine wave, so we need to measure the AC also, AC analysis, so we have selected AC also. Now once you have selected the analysis types, so you have to plot the results. So how to plot? So you have to go to output, so you have to select to be plotted on the design, right? Select on design. On the design I need input on the graph, and also the output. Only input output I need, so I have selected input output lines, right? If we come back here, so it is automatically selected both input as well as output. Net 6 is the input line, V out is the output line. Now run for the simulation, select this and run. So once you run, so we have got the output. Okay, just double click here, so maximize it. So if you select this, which one, yeah, if you click on this horizontal, so here it is showing the vertical lines. So now if you click on this, so all the analysis will be showed separately. Just click this, so you can see here, right? Now if you want to analyze it, so just select the window and split it. Fine. Now if you observe here, so in the AC analysis, so because it is basically a voltage amplifier and basically it is common source, right? Its voltage always be in negative, so just remember this, because the gain will be in negative, right? If you observe here from here, so voltage will be, so your signal will be out of phase by 180 degree, right? If you observe here, see, input is given like this, so output is starting from here, right? And also if you observe the calculations, right, so just see here, so the input voltage I have given is millivolts, right? Millivolts from 5 to 5. 5 to 5 means the total peak to peak voltage I'll get 5 minus 5, right? Peak to peak voltage means 5 minus of minus 5, that means I'll get 10 volt, right? If you just take an editor, I'll just take that, yeah, office, yeah, I'll show you here. Just see here, here the V in, so V in peak to peak voltage, if you get, see here how much you are getting, this is 5 and minus 5, that is 5 minus of minus 5 voltage means you will get is equal to 10 volt peak to peak you will get, right? So this is this is 10 volt peak to peak you will get, right? This is the V in, right? In the same way, if you observe the V out, because it's a voltage amplifier, if you observe here, so here the input voltage is, so the peak voltage is, it is showing 345, so almost at this point 344.6 millivolts, right? So that means this is V out peak to peak, V out peak to peak, it is 344.46 minus how much it is, if you observe here, it is 320.5 millivolts, right? That means 320.5 millivolts, right? So that means if you minus this, you will get how much, 24, around 24 point something or 24 you will get. That means for 10 volt peak to peak you are getting 24 volts peak to peak voltage, right? That means if you calculate the voltage gain, right, so voltage gain would be, is equal to what? Voltage gain is V out by V in, right? So if we calculate for that, V out by V in, 24 by 10, you will get 2.4, right? So this is the gain for this. That means for 10 volt you are getting 24 volts. So this is how to analyze the code, so how to analyze the output. So this is the voltage gain of this. So 22.4 voltage gain I am getting, right? I'll just close this just for your understanding. I just saved this, fine. Likewise, so if I just extend this here also, if you observe, right, see the gain in the AC response, the magnitude I am getting is 2.4, right? Slowly it has decreased, its frequency response is decreased around at some point. It started decreasing at 11 megahertz, so started decreasing up to 15, right? In the same way for AC response also, sorry, DC response also, the gain you are getting is around 2.4, okay? So this is the operating point, 121 millivolts and 45 millivolts on both x and y axis, fine. So this is the pre-layout simulation for common source amplifier. I'll just print this file, I'll just save this in test VLSI. I'll select common source pre-layout simulation. I'll just save this. Likewise, you have to should save the file, okay? So this is a complete pre-layout simulation of common source. So in the next video I will show you the post layout simulation of the common source.